Welcome to the Egg on Air live session with Anthony Agnone. I'm Gia Mirando, Director of Marketing here at Dataiku, and I'm thrilled to introduce Anthony as he discusses building authentication and fraud detection solutions for the enterprise. Happy to have you join us today, Anthony.
Thanks, Gia. Happy to be here.
So before I officially pass the floor over to Anthony, I wanted to share a bit about his many accomplishments. Anthony is an applied research engineer who enjoys working at the intersection of machine learning and software engineering. He holds an MS in Electrical and Computer Engineering from Georgia Institute of Technology with specializations in digital signal processing and computer science and certifications from AWS and Udacity. Anthony currently works in the areas of machine learning engineering and cloud native development to seamlessly embed decision science into software products for clients. So without further ado, Anthony, I will pass the floor over to you.
All right, thank you very much. So as Gia said, nice intro there. My name is Anthony Agnone, and I'm currently a machine learning scientist and engineer. Let's just get right into it. So just a little bit more of a background for me. Like she said, I have an MS from computer engineering. It started really with a focus in signal processing, right? So it started with circuitry, but then turned more into, analyzing audio. And then, that turned more into, having features from audio. And then that led into machine learning. And that was really my focus in my master's year, was how you really take machine learning, not only to do, signal processing methods that led to machine learning, but also combine that with software engineering, right? And make that reproducible. Coming out of my master's, I found a small company called Pindrop in Atlanta, and they do a lot of both fraud detection using audio techniques and non-audio techniques, as well as authentication for the same type of data. So I have recently left the company. So some of this content may be related to some of the topics that we worked on there, and some of it may not be. And aside from work endeavors, you can find me blogging and doing a weekly newsletter related to machine learning and engineering at lifewithdata.org. All right, so let's just take a step back real quick. So we have, in the enterprise world, we have authentication, right, of genuine customers, and we have fraud detection, right? Let the good guys in and keep the bad guys out. So who really cares about that, right? Is that just a problem for for big banks and just let them handle it, or who should really care about this? Well, I claim that really everyone should care, right? Because whether or not you are working at these huge companies or not, at this point, most of your accounts have gone online, right? Or they are at least digitized in some way. So, a lot of your assets and things that matter to you are protected by these accounts, right? And you need ways to access these accounts. And, that could be online through a web portal. It could be through, a telephone. And when you call, that goes through a call center, right? So, big companies have these massive call centers, and some of them are new, some of them are a little bit dated. And they have varying measures of, protection and security in them. Okay, so with improvements in web technology, the defense mechanism of online tends to be a little better. But for call centers, there are definitely still some weak points, especially as companies are trying to innovate and kind of revamp their call centers. There's always going to be points of weakness. So there, in the fraud detection side, millions on millions of dollars can be saved annually in ensuring this kind of protection, right? And of course, we can use various techniques, and a lot of them include machine learning, to be able to detect the kind of fraud that seeks to expose these security points and take good customers' assets out of their accounts. Okay, fraud detection by itself is easy if you look at it in a certain way, right? If I want to have no fraud happen in my call center at Bank X, I will just say no to every single call that comes in, right? But what's the problem? You will not authenticate any of your good customers, right? So that is just as important of a cost to deal with when you are running your call center, running any sort of access-based flow for your customers, right? So you also want to pass in, as many as possible of your genuine customers. Of course, that can lead to, millions and millions of dollars being saved annually, right? In efficiency, right? You want to let your genuine customers go through your authentication process feasibly as fast as possible, right? While still protecting their accounts. So you always have this balance, right? You want to stop the bad guys when they come in, and for everyone else, come through. We want to get you to your account and get you to do whatever you need to do with your account quickly. Okay, so we know there's this big trade-off, right? We want to stop the bad guys. We want to let the good guys in. We want to get them through quickly. Easier said than done, right? So when you are bringing machine learning and any automatic computational techniques to accomplish both of these tasks for companies, there are a lot of trials and tribulations that go into the products that do that. So I'll talk at a high level through the next couple slides of what are some of those problems, and especially as it relates to the problems that you face when implementing algorithms to do this. Okay, so first and foremost, maybe the entry level problem that most people are aware of when you deal with fraud detection is label imbalance, right? And by that I mean, for your call center, when you are trying to catch any fraud that might be going through that call center, almost every single call is going to be genuine, right? I mean, unless you are, maybe a bank that almost everyone wants access to, that fraud is going to be really rare. So, as a really quick way to get, in this example, 99.8% accuracy, just let everyone through, right? It's the inverse of what I said before. If you want to authenticate everyone, it's easy, just do it. Don't even check, but you won't catch any of the fraud, right? So if you don't do this fraud detection carefully, you can think that you have stellar performance, fantastic performance, 99.8% of the time you're right. But what you really care about is that 0.2%, right? And if you are wrong 100% of that 0.2%, that is the millions of dollars that are lost annually. That is someone logging into the retirement account to see that all of a sudden it's zero. So it's a big, big problem, and you need to be very careful about it. Okay. Another big issue is label bias, right? And what I want to keep this separate from the issue of bias and fairness. We'll get to that a little bit later. But let's say we have a sequence of calls that come in, and these could be from multiple customers. So look on the left, we have a series of different calls. We have for each of those calls, some estimate based on our algorithm of how likely it is that this call is fraud, right? So let's say this is from a population of millions of calls, and we just rank order them. Let's just look at the riskiest ones. Let's take the highest probability of fraud. We're going to send those over to whoever needs to give us the intel on that, right? Usually it's an expert within an organization that can go in with much more data than we have with the algorithm into client accounts, and really tell us, be an oracle in a sense. Tell us, really, is this fraud or not? And that's great feedback, because when it's confirmed to be fraud, then we say, great, all right, what we did during the last model training sequence was good. And then for the false positives, we say, okay, good. Now we know to tone down what led to some of those calls being claimed as fraud. And for the false negatives, of course, it's just as important. We know we see new fraud, new weakness points, and we can adapt based on that. Now, what happens when you can't have an expert fraud analyst analyze every single one of your predictions, right? You have thousands or millions of calls per day. You're not going to have people going in and labeling every single sample, right? So big efforts that have been underway, to have these huge data sets, that are labeled. That's great. It's not always feasible. It's very, very expensive to have full labeling of these data sets. So what ends up happening is, as you might expect, and as you might think intuitively, you just want to review the most likely to be fraud first, right? So clients will go and they will do that. But at some point, they can't get to all of the calls feasibly. So what happens to those calls? Those might be the more important calls to get feedback on to better your algorithms, right? Because at some point, you're going to know for sure, based on these calls that are 99.9% likely to be fraud, you know that those are going to be fraud, and they might not be the most important types of fraud. So if you're not maybe tagging types of fraud, you may end up with that 94.2% likely to be fraud call as extremely important relative to the 99.9% that you're pumping through. And the client says, hey, you know, these fraud calls that you're giving me, they're obvious fraud, but I care about these other ones that were 94.2, 93.8. So you have to be really careful about these self-fulfilling prophecies, because if this cycle keeps happening over and over again, where you're only getting these top K calls reviewed, then more and more you're just going to be tuning your algorithm to fit to that, right? And you're going to start to miss more and more of that fraud that never gets reviewed, and its probability of fraud is going to keep going lower and lower. Okay, another big issue is in general, it's non-stationary data, right? We have a cat and mouse game with fraudsters. Some machine learning and data science problems are a little bit simpler in a sense, right? Because you are trying to predict something that, although there's always going to be things like covariate shift and just shifting of your data's distribution, it's much different when that data itself is another living, breathing organism or set of organisms, right? That is much more non-stationary data than something like, oh, let's predict whether this population of images is a guy or a girl in the image. So let's look through this fraud cycle. Starting at the top left, let's say that we have a fresh batch of false negatives that came in from our client, and we know, okay, here's some new fraud calls that our current training cycle isn't really detecting. So we need to change something, right? We need to somehow inform our model training process, maybe it's new types of data, maybe it's a different way that we're going to be doing our training to be able to better detect that fraud in the future, right? So we go through that little bit, and then that's our catching up phase. So this is good guys catching up. On the legend on the right, you see good guys. It's kind of a split brain of like a digital brain, and then just an actual biological brain. That's because there's part of it that's an automated algorithm training process, and part of it is very much the researchers that are informing that process. And on the left, you have fraudsters, which, it's a person. They are there on the phone trying to get through the security of the call center, but they might be using technology themselves, right? So, in this good guys catch up process, eventually, we keep training, we inform and improve our training process, and then we get to the bottom right, which we would call advantaged good guys, right? So we have either novel behavior or adapted behavior that gives us the upper hand, right? Now we are frequently detecting the fraud, and we're sitting pretty, we're on top. But notice that again, this is very non-stationary. There's an actor on the other side of the fence who very much is against you, So he is doing the same thing. He may or may not be doing machine learning techniques. We've only seen some level of extreme technical prowess, at least in the fraud that I've personally seen. But there is still an adaptive mechanism that's happening on the other side. So this is an eternal cycle. It never stops, right? So it's not going to be equal lengths. We of course want to reduce some of these cycles down, but this is always going to be an issue. All right, so those are 3 core issues with fraud detection. Let's go into more on the authentication side of things, right? So here's just a simple diagram that describes what data flows would look like in an IVR, an integrated voice response system for a client, right? So that you call in and to anything, bank account, insurance, whatever. And they say, press 1 if you want to do this, press 2 if you want to do that, right? So that's just you poking numbers on your phone. That's one form of data. There's also, say this, or, say your number, or say your name, in order to continue. That's another type of data, right? That's voice. There could be other types of, data where you even, take a picture of yourself, send an image to truly confirm identity. You could be eventually answering questions, right? So that's knowledge-based authentication. And that's not just your voice, it's the information you're using to answer those questions to continue. So The problem here when it comes to doing any sort of data-based algorithm to automatically or more quickly authenticate people is this very, very diverse data, right? If you view this as a tree going from left to right and you're looking at the leaves of the tree, all those endpoints or different points where you want to invoke your algorithm and get a certain score to see if you can speed up the authentication process, you're going to have much different data in each of these leaves, right? There are going to be some of these paths that have only DTMF tones. There are going to be some of these paths that have only voice, and so on and so forth. So how do you handle that? Do you have just one be-all, end-all model to handle all these cases? Do you want to have more fine-grained models and handle specific data cases? What if you get into hundreds or thousands of different models just to handle all these cases? You have to choose a point on that spectrum between one model and I want one model for every single possible path we can have. Another big issue with authentication is depending on the setup of your client and how you have set up just your process, you may not have the most direct of feedback, right? I mean, think about when you call in and you get the fast track because maybe you answer some questions right, or your client has a voice enabled IVR. You're going to get fast tracked, and then how do you think that feedback, that positive feedback, gets back to the algorithm? There might not be a super direct label, for lack of a better word, to give to your algorithm, other than something like missing complaints later on. So if you see that fraud happens on your account, you're immediately going to call in and you're going to notify the client and say, hey, this is definitely fraud. Okay, that's a good way to go back and backtrack and say, hey, look, this authentication was granted, but then fraud came back in on the account later on. That was bad. But other than that, you may just want to assume some soft definition of, okay, yeah, that was a good authentication because we had high confidence, nothing bad happened afterwards, and the credentials matched what we had previously seen. But notice how I said soft definition. You're now departing from the comfort zone of having labels for all your data, and you're having to propagate labels, or you're having to guess labels, and that changes your algorithmic setup. Okay, there's also a lot of psychological barriers, right? We are, in a still a very technical phase of machine learning, right? Things like machine learning ops and machine learning engineering are making things simpler, but the field of machine learning it's rampant with new algorithms and new ways of doing things, and very technical, right? So it's not easy to kind of boil the ocean down to make perfect sense of all this to clients, right? So you have this innate trade-off of, on one hand, on the y-axis, you have interpretability or explainability of your models. And then on the x-axis, the trade-off there is performance. So if you wanted to start with, okay, I need something that is just the most explainable and interpretable, and exactly what it's doing, and you can, derive it really easily, that's in the family of generalized linear models, right? So something like a simple regression, you can look at the coefficients of that regression, and you can, do things like have immediate notions of feature importance based on that. That being said, you're only going to get so much performance, right? So then you're going to say, what, I need a little bit better performance than this, or I need a lot better performance than this. How do you do that? I mean, there are many ways to do that than just having linear models. The problem is, as you use some of these more advanced and more modern techniques, like using kernel-based methods, tree-based ensembling and deep neural networks, almost definitively you have a reduction in interpretability as you increase your performance, right? So, I mean, there's some really good work being done in interpretability of deep neural networks, but it's pretty young, and especially from the standpoint of having to use these things at an enterprise scale, right? Okay, so those are some core issues that you can see. Hopefully, I'm painting the picture well for you to where you have business problems and you have really, really good, strong field of machine learning, and you can kind of see how these problems kind of naturally map back and forth between the business domain and the technical domain. So what are some of the ways that, the technical innovations in machine learning are helping, these very natural problems that arise, right? So we mentioned label imbalance, right? Some of the, most direct ways are really useful. And, these are still a little bit of classical techniques, but of course there are more and more dynamic ways of implementing these somewhat classical techniques, right? So you have, millions and millions of genuine examples, right? You're trying to do fraud detection. You really care about, the in this case, the positive class or the minority class of fraud, right? You can probably, use many less samples of the genuine class, that majority class, boil it down to much fewer samples in order to, restore some balance, as it compares to how many examples of the fraud that you have, right? That's pretty straightforward. That's, there's not many issues in doing that. Usually you have so many samples that, you can use a number of techniques to get a good representation of your majority class while you're doing downsampling. Now, upsampling, it seems like just the mirror image, right? Oh, that's great. We can downsample our majority class. Well, let's just upsample our minority class, tried and true, one call to, our sklearn library in Python, and we're done. It's not that simple for upsampling. I mean, think about what it means to have a minority class. You have, so fewer samples than your majority class. And depending on your application, especially if it's fraud detection, you could have 1, 2, 3 samples. So, when the notion of upsampling, that carries a lot of baggage. How are you doing that upsampling? If you have, let's say you've downsampled your genuine examples to 50,000, 100,000, right? And you only have 3 examples of fraud. Okay, so if you want to have a perfectly balanced data set, okay, you're going to upsample your 3 examples of fraud to 50,000, 100,000 examples of fraud. Okay, but you're upsampling from those 3 examples, right? What if there are 3 very similar examples and you're just all of a sudden creating 50,000, 100,000 examples of this one type of fraud? There are types of fraud that you haven't even seen in that sample. So, you don't just want to create a massive amount of the same fraud. That's only going to get you so far. So you have to be very careful when doing some of these techniques. Another one that comes in is just weighting the samples, right? So you can just weight by an inverse of the imbalance that you see. That's, it depending on how many minority class samples you have. Sometimes that's a safer way to deal with this imbalance, because you usually have some sort of random based technique to do your upsampling. And if you don't have enough confidence that that technique will yield credible synthetic samples, then you're better off just having a weighting technique to protect yourself. Okay, another issue with the label bias, right? How do we deal with the fact that we might not always get feedback for some of the more important samples, right? So one of the main ways to do this, you could do label propagation, right? So that's using labels that we know we have. There's sometimes they're called hard labels, and you create soft labels based on that, right? So this image here, it's using a graph-based technique to do label propagation. But if you have nodes and you can define some notion of having neighbors, right? You can infer clusters is the term here, but you can say classes. You can infer the class onto the neighbors of those nodes, right? There are some other ways, such as using actually more explicitly modeling the oracle, right? And that's active learning. We'll get to a little bit later, but if we treat that fraud analyst as an oracle, we might not always just want to give the oracle the highest probability sample to be fraud, right? What we really want to give that person who's going to do the work, or give that entity who's going to do the work to, it's effort, who's going to do the effort to get you that label. Maybe you want to give them the sample that you have the most uncertainty about, right? Because once you have reduced the uncertainty of your algorithm, then you have a much better algorithm than if you just kept giving the highest probability to be the positive class over and over again. Okay, so remember, non-stationary data, we have this cat and mouse problem. What are the ways that we can reduce this, right? Of course, you can just bring a better model, bring better data, and that'll just, help you be better and beat out the bad guys. One way to do this too is just have a really good model retraining process, right? If you have a really good repeatable pipeline that can, on a decent basis, recurring basis, just keep training models, you can adapt faster and faster to these changes in the fraud landscape that happen, right? So, sure, there are always going to be some level of false negatives, for any sufficient level of, fraudster prowess, I'll say. But you can react to those much, much, much faster if you have an automated pipeline in place that can, continue training these models and have an automated labeling mechanism or some way just to get that feedback to form the recurring data set to train your new model. There's going to be a really good diagram for MLOps later on, and this will come to fruition and give you some better imagery. But having that repeatable pipeline in place, it's the same benefit as when you have DevOps, and you can just make one small change in your source code. You can have it tested, and you can have it immediately deployed to an environment where someone can do some more manual UAT testing. Okay. So, I mentioned DevOps. This is another great way to handle your diverse data problem, right? So, this doesn't solve the problem for you that I mentioned before of you need to decide where you are on that spectrum of I just want to have one grand model versus I want to have one model for every conceivable combination of data that I'm going to have. But it becomes much easier to manage these models if you have really good ops practices built in to the whole process, right? I mean, if you have, let's say you just ended up with 13 models, right, for all these different data scenarios that you're going to face. If you have a really good pipeline in place, whether it's on premise or in your cloud, and you have these models retraining, and every time they retrain, there's a lot of testing and no bad model gets put into your production environment, and how the simulated performance is going to be, you are measuring in production how the actual performance is, it becomes much easier to handle these diverse data scenarios. And especially as the data distributions change, right? Having that reproducible process in place can help prevent, any doomsday things from happening when, the client's data distribution, suddenly changed. We need to pull you off this project and put you in so you can come in and save the day. Save the day up front. Get your pipelines in place, and the day will stay saved, and you can focus your energy on the next big thing instead of just a little thing because of a mistake that you of something you didn't do earlier. Okay, missing labels. All right, so I kind of touched on this before, but there are a lot of semi-supervised learning methods to deal with this. These can be label propagation. These can be like the Oracle-based. But another cool one is generative modeling. So we're getting there with audio-based and voice-based techniques, but it's of course hit the world by storm, at least from the marketing perspective, how you do these things in images, right? So, here you just have a way to have style transfer. So you have, a painted image of a riverfront, and you have, some notable style that you want to map onto that riverfront image. And you can do that, right? That is a completely synthetic sample on the right. And similarly, things like generating faces, right? Setting aside the ethical concerns of that, it's pretty fantastic, just the level of of detail and realism that some of these algorithms are making. So you can use these same techniques to be able to create your own synthetic examples, right? So even though for any given fraud event you might only have a couple samples, over time as an enterprise, you're going to start to accumulate a nice number of samples in general of fraud, right? And then once you have enough of those samples, you can start to synthesize some more examples. And you can even use those synthesized examples to inform yourself of fraud that may start to exist but hasn't yet, right? So it really starts to bridge the gap between technical skill and creativity when you can leverage some of these generative methods. Okay, so again, how do we deal with some of these psychological barriers, right? If you view that trade-off of explainability versus performance, you're going to have to choose a point on that, Pareto optimal curve. You're going to have to choose a point on that efficient frontier where you say, okay, given the performance that we need, we want to make our model as explainable as possible. Okay, and there are ways to do that. Same way with interpretability, right? You just need to know the methods for each type of model, right? The way that you're going to introduce trust in your model for a linear regression is much different than how you're going to do it for, say, a deep neural network, right? For linear models, you're going to have a much more hands-on, kind of out-of-the-box mathematical way of doing things. And for deep neural networks, it'll be, a little bit more Monte Carlo focused and more of, this tends to correlate with that when it comes to input output of your black box, right? But just, the order of things here is you need to choose the point on that curve of what kind of performance do you need or what kind of interpretability you need. And then based on that, you know how to solve for the other axis point. Okay, so those are some of the innovations that we've, as a community have been doing so far to face these problems of, balancing fraud detection and authentication. But there are more things on the horizon, and these could definitely be applied, right? So, I kind of jumped the gun and mentioned this a little bit, but, with active learning, you can have human in the loop modeling. We've had so much of a focus on how machine learning can automate things, right? But think more maybe about how machine learning can make things better, right? So instead of just automating 100% of authentications that come through, what if you could know, let's say that accuracy is 95%. What if you can know that it could be 99.8%? And, there is a little bit of, human in the loop there. So you're building your model, and when you're trying to give feedback to your model, you really want to take the uncertainty of that model's predictions and use that to direct the effort of getting labels, right? Getting labels is not always cheap. Sometimes it's really expensive, right? So really, you don't always just want to be giving, your best bet of, 99.9% fraud. You want to be giving it, hey, I'm really unsure about this, and there's a decent probability of fraud. We really should look more into this because one, it might end up being fraud in this case, but two, once I have this feedback, I can really improve how the model is trained the next time. Okay, so this, I think this is really more a forefront. I haven't seen too much work here, but the multi-agent reinforcement learning field is getting really large, and there's some really fantastic work coming out of a few different research organizations, and even I've seen some Salesforce research. It's great because this is bridging the gap further between machine learning and reality, right? I mean, it's not just one actor being your agent, being your machine learning algorithm in the environment. Really, there are multiple agents, and that is no more true than in fraud detection, right? Because the fraud that's being committed is itself an agent, right? So your algorithm is one agent trying to detect the fraud, and you have many different agents that you're up against. Being able to explicitly model those actors in your algorithm is bound to give you a performance boost. Okay, so another big issue is controlling the bias of your algorithm and ensuring fairness, right? So it's kind of been, to date, it was a slow, but as you can see on the plot on the left, it's been kind of an exponential increase. And note that ends in 2017, so that trend has only continued through 2020. Bias is a big deal, and it really was underestimated, and finally it's getting the level of criticism and attention that it deserves, right? We were very much through, or maybe even past, the era of what can we do with machine learning. It's quite clear that, especially with AlphaFold coming out, it's quite clear that most things will be possible. It's just a matter of when. Okay, so the focus really needs to shift now to how do we do these things? Who gets to do these things? How do we verify these kind of things? Because machine learning is now being used, across the world for really important questions. who's going to commit a crime? Who do we think is going to commit a crime, right? You've seen how these things are biased towards ethnicities and economic backgrounds. Who's going to get approved for good housing? How do we rate teachers? Who should get career opportunities? These are core problems that have historically had bias, right? So we thought that, or at least some of the messaging was that machine learning would fix a lot of these problems. Machine learning has not fixed these problems, and maybe it hasn't necessarily made them worse, but it's almost automated the problem and hasn't made it go away at all, right? So the quote here below that I really like is, any data we give the algorithm is describing, whether directly or not, the choices that have already been made in society. And think no further than the labels we give the algorithm, right? So you might have inductive bias of the algorithm you're using, right? That's one thing. But even if you have a perfectly unbiased in terms of inductive bias, for lack of better for a contrived example, you're still going to have some of that label bias, right? Because we are telling the model what's right and what's not right, setting aside some unsupervised learning techniques. So we won't be able to just hand our problem off to data, because the data itself has already encoded those biases that we as a society have put into it. So we need to be very careful both in how we are structuring our algorithms and how we are pumping data into these algorithms, right? Because both of those things contribute to a lack of fairness in our modeling. Okay, and then at the end of the day, really, let's say we solved all the problems that that I've mentioned before. We have to keep increasing our MLOps efficacy. And some organizations have really ramped up the quality of the work that's being done here, and it's great. But things to look out for in this diagram, that aren't necessarily part of standard DevOps, or really, you can see it maybe as an extension of DevOps. You have things like feature stores, you have things like model registries, you have machine learning specific prediction services, right? These are, some people say that MLOps really isn't new, and I think that it's there's not too much of it that's brand new. I think it's really some extensions of DevOps. So DevOps is a really beautiful thing. It has really brought engineering forward, and really those techniques are really just being applied into MLOps. And if you read some of the articles online that are being posted by large organizations, like Netflix and Stitch Fix, it really is helping their workflows a lot. So we're definitely going to see a lot of these things moving forward. And it's going to help a lot when it comes to sensitive things like protecting everyone's digital assets. Okay, so I definitely went through a lot there, but I hope you guys enjoyed this talk. I'm happy to go into some Q&A. You can find me on many different platforms, but if you just pop into lifewithdata.org, you'll be able to hit some of these other links.
Great. Thank you so much, Anthony. Fraud detection, always obviously a very hot topic, and appreciate you sharing all of your insights with our audience. We have some great questions that have come in so far. I want to encourage everyone else who is listening, please continue asking your questions, and we will try to get to as many as possible. Let's dive in. First question from Anna. You mentioned examples of the fraud detection use cases being implemented across various industries such as finance and insurance. What other verticals have untapped potential for fraud detection?
Yeah, that's a great question. So I can only speak probably at a high level to this, especially because I don't want to expose any IP for pinch off my previous employer. But what I can say is that what we saw, going across a few different verticals, is that if you have the fraud problem, your industry is ripe for solving it. What really sets apart the attempts to solve the problem are how you approach it as a joint collaboration between who's running the algorithm and who the client is, right? So for example, in banking versus insurance, right? Banking, much higher fraud rate, much more budget allocation that's going towards solving these problems. With insurance, it's hit or miss. It depends on the reputation of the company a lot of times. Some companies are very focused on reputation, and they're more than willing to put out that proactive budget to have the labeling resources in place, to set up the right infrastructure, to make sure things are done the first time. But if the budget isn't made, or if the mental effort isn't put in, prioritization isn't put in, then you're going to have trouble fixing your fraud problem. But as far as which verticals needed or appropriate for it, as soon as it's enough of a problem to warrant going after, it can be done. It just needs the right effort put towards it.
Yeah, absolutely. Great. Let's see. Next question is from Katie. Especially in the current environment, we've seen a lot of businesses struggle with the pitfalls of models or systems that are ill-equipped to handle changes in the norm. What do you find is the best solution to overcome this and infuse adaptability?
Yeah, so two parts. The first part is the term of MLOps, right? So you're always going to have change, right? So when you're learning these techniques, you're usually taught like, hey, keep training different things, do your hyperparameter optimizations, and once you have a good candidate, right combination that leads to a certain performance, there you go. And then that's it. So the problem is you need to model that change up front into your system, right? So you immediately need to think about, okay, how do you update that model? How do you recreate that process over and over and over again? And that's where MLOps comes in, because if you've appropriately modeled your environment, you have modeled, when, where, and how those models get updated to deal with, changes that happen. So the second part of that is, there's typically, historically at least, been like a focus on algorithms instead of data. And you very much have to focus on data. And by that, I mean, you can, with most machine learning problems, besides the absolute forefront of the field, if you have the right data, you do not need the most, the crazy big banger deep neural network. You can solve it with a regression or, simple tree-based algorithms. People focus so much on the newest, coolest algorithm, but you have to focus really hard on the data. And it's not just what type of data you get it, it's about how to consistently extract that data from the real world and do it in a reproducible way so that, when I train my model this week, I have a similar amount of, quality audio that has been given to the algorithm as it was last week. Because if you have the same algorithm and all of a sudden you just rip out all the audio and all it gets is, text or something else, you're going to have a very different performance.
Right. Let's see. Next question from Myra. How can organizations ensure that fraud detection systems that get implemented stay relevant, i.e. are regularly evaluated and updated?
DevOps. So I think one common thing that I've seen is, you have really smart people in an organization, and you employ them to build a really good machine learning framework, right? And they will do that. It may be to various degrees of efficacy, but what I think the mistake I've been seeing around the industry is there's not enough DevOps focus being put on the whole process, right? It's usually been, let's have this research and development, or this research been done, and then we're going to kind of toss it over the fence and just magically have it happen in production and give it to our products. So what you really need to do is have those best practices of DevOps from the get-go. And the reason I harp on this again is because it's not just having your production be MLOps oriented. It's about having your whole research pipeline be DevOps MLOps oriented. Mm-hmm. Even if you have the shiniest, most beautiful production workflow, you could end up with almost no backlog of innovation because you don't even have the right research infrastructure in place. Right. So it's not just about having everything beautiful in production. You want your researchers to be really effective. And that doesn't always mean have every person doing machine learning research be really good at DevOps. That you don't want to do that, because you're not going to get the right kind of machine learning talent if you expect everyone to be an amazing engineer at the same time. So we need to embed more DevOps minded people into machine learning research departments.
Great point. So I think we have time for one more question. This question is from Erica. What have you found most successful in accounting for false negatives or false positives in models?
That's a great question. So two things. One is it's very much meta of your algorithms. Some of the biggest success that I've seen happen in being able to either detect a new kind of fraud or find a new way to detect, a really hard to detect type of fraud is, take in the data that you're getting right now and think about the latent factors of, what kind of fraud is being committed. What is that actor in real life doing? It's not always about how do you normalize and clean and prepare your data. Sometimes it's like, hey, what if we could take this data type and have it appear to the model? And that's totally out of the box, because you're completely changing your machine learning problem. In academics, you're always given this type of data, now make it work. But in the real world, it's like, wait, what if we all of a sudden had this new type of data input, and then your performance just totally jumps up? That's been a really effective way at reducing the ways in which we miss fraud or fail to authenticate someone. And then back to taking our mistakes and how do we improve on them. I think one thing I didn't mention before with some of the semi-supervised learning techniques is perturbation of the samples that we do have, right? So if you have certain types of fraud and you have these data clusters, and you want to say, oh, well, what else could be done in this space? The notion of perturbing those samples, you just like poke them and change them a little bit, and you say, oh, wow, okay, so it can happen a little bit more like this. And it's kind of a new way of creating new samples. And just doing that, that's, of course, that has no real supervised aspect to it. You're just creating new samples, and that helps us to, detect that fraud better in the future, or detect the authentication better in the future.
Well, unfortunately, we are nearing the end of our session. Thank you, Anthony, once again for sharing all of your insights and actionable takeaways with our audience. And thank you to all of you who joined us live today. This will be our last live session for 2020, but we will be back in January to kick off the new year with some incredible new speakers and episodes. So stay tuned for more information on that. Until then, wishing everyone a happy, healthy, and safe holiday season, and we will see you on air soon. Take care.
Thank you.